Okay, in the video today, we are going to cover a specific type of polygon called the quadrilateral. So we talked about polygons, different properties that they have. I'm including a previous video on 7.2 if you'd like to watch that one. That one's all on parallelograms. This one, we're going to try and condense this just with how we've had to condense kind of our learning this year with not having Fridays. So I've just put all of these on one page and we're going to practice using them today in a regular plane. So not putting them on a coordinate grid, just understanding the properties and the relationships between these different types of quadrilaterals. So on this flow chart here, first of all, I've defined quadrilaterals. So remember, a quadrilateral is a polygon that has exactly 4 sides. So any polygon with 4 sides we call a quadrilateral. This is kind of the flow chart. So here's a bunch of different types of quadrilaterals that you can see here. And then there's different special types. So headed down on the left, we have what we call parallelograms, and we're going to talk about those first. Parallelograms are then going to include rectangles and rhombus. And then we'll talk about how a square comes together with both of those. A trapezoid, here we'll talk about that one, is a certain type of quadrilateral that is not a parallelogram, and even more specifically, there's what we call isosceles trapezoids. And then the last one we're going to cover is a kite, and we'll just cover these very simply. We'll see them again when we go ahead and calculate volume, but mostly just to make us familiar with these properties, so if that was something that came up on an ACT, we'd be able to answer such questions. So let's start with this first stem with parallelograms, okay? And I've put this one off to the left. Again, if you're just taking these on a blank sheet of paper, great to draw what you need or what you feel like will be helpful. So first of all, by definition, a quadrilateral where both sets of sides are parallel makes a parallelogram. So you've got here, these two sides are parallel, and then you have the top of our parallelogram also parallel to its opposite side. So we probably should have 2 on there to show that those are parallel there. Now, parallelogram, as you can see if you watch the video 7.2, is really just 2 sets of transversals. So I'm going to draw a little diagram over here. If I have 2 sets or 1 set of parallel lines and then another one coming through, so there's my transversal. Remember, we talked about if this was, say, 45 degrees, this one's also 45 degrees. Same with these ones. Oh, not that one. They're vertical angles, sorry. And if we add another transversal that's cutting at exactly the same angle, wow, that's the most parallel line I've ever drawn. Okay, then these are also 45. So we're including all of those as also 45 degrees. And then remember to find the linear pair or the obtuse angle within our transversal angles. We do 180 minus 45, which would give us 135 and 135 in all of these obtuse angles. So what I want you to notice, the parallelogram is really just this part right here. So if you look at that parallelogram, you'll notice specifically with the angles, opposite angles are always the same because of this relationship with transversals. And this one right here, always the same, right? Opposite angles. And then you'll notice that these are what we call adjacent or consecutive angles, and those are supplementary. They'll add to 180 because they represent that linear pair. So you have a few of these relationships listed out here. Angle BAD, so B to A to D is this angle here. And it says it's congruent to D to C to B, so it's opposite angle over here. ADC, right, looking here, this angle is congruent to ABC, which is the angle here, so we know that these opposite angles are congruent. It's also true, right, that if we have a parallelogram, opposite sides are the same length. So A to D, you see these little hash marks there, it means that's equivalent to B to C. So that would be one that we could add in here that's not included. AD is congruent to BC. And we could also say that AB then, going down the left side, is congruent to DC. So those are true. And then, so those are some things we could list here. And if you want to write them out in words, you could there. We could just say, right, each pair of opposite sides are congruent. each pair of opposite angles are congruent. Maybe I'll write it out really quick. Of opposite sides are congruent, and opposite angles are congruent. And then again, we would call them consecutive angles or adjacent. So consecutive meaning two angles next to each other. So, or adjacent angles. They're supplementary. Oh, I should say are. Supplementaries, right? So they add to 180. Wow, if you can read my handwriting. And then the last one, these two properties or these two statements right here, AX is equal to CX. AX is equal to CX. You'll notice that these diagonals are not equivalent to each other, but they do bisect each other, meaning they cut each other in half. So this length right here is equivalent to this length right here, or congruent. So we do know that diagonals bisect each other, so that would be kind of our last one here. So if you know they bisect each other, then it's going to be a parallelogram. And really, as long as you have one set of sides that is parallel and congruent, it forces the other ones to be also congruent and parallel, so it creates a parallelogram, okay? So that makes up a parallelogram. Once we know it's a parallelogram, then if there's some other more specific things, it can create a rectangle or a rhombus. So a rectangle, by definition, is just a parallelogram with 4 right angles. So all of its angles are 90-degree angles, and the diagonals are congruent. So yes, they still bisect each other, but those diagonals are actually exactly the same length because now we've straightened out all those angles to 90 degrees. So those are the specifics that make it a rectangle, as well as a parallelogram. A rhombus then is a parallelogram with 4 congruent sides. Okay. And the diagonals on this one are actually perpendicular. This little symbol means perpendicular. So you'll notice here, these diagonals are crossing. Oops, that looks terrible. These diagonals right here are crossing at a 90-degree angle. So as soon as you make all of these sides the same length on a parallelogram, it creates perpendicular diagonals, which is really cool. And you'll notice that these diagonals are creating angles over here. It's actually cutting the original angle in half. So whatever this angle was, angle H, angle 8 and angle 7 are equivalent and just have cut it in half. So you'll notice here that those are going to be the same. So 5 and 6 and 7 and 8 are equivalent. So we could also state that diagonals bisect the corner angles. I'm sure that's a great technical term. Okay, lastly, they're parallelograms. So if it gets even more specific, a square is a parallelogram that is both a rectangle and a rhombus. So if all the sides are equivalent, right, and the diagonals are congruent, you've then created a square, and there's right angles on all the corners. So a square fits the description of all of these properties in one. Then it can be considered a square. Okay, so there's our properties of parallelograms. Kind of a condensed version, but you can look back at those diagrams hopefully, and that helps. Let's jump over to trapezoids. So you'll notice we're headed down this stem now. A trapezoid is a shape or a polygon with exactly one set. So this one is a quadrilateral with exactly one set of parallel lines. So this time, kind of the same idea as our last one. If I have a set of parallel lines, I'm going to mark those as parallel, and there's a transversal cutting through. This is creating essentially one side of that trapezoid. So you'll notice that angle relationships of a transversal are going to hold. Whatever this one is its supplementary angle. Those are consecutive interior angles. But the other line that's coming through is just no longer parallel, like a parallelogram. So this transversal is cutting maybe at a completely different angle, and again creating its own angles over here. But again, his angles also would be supplementary over here. If those are cutting at the same angle, then it creates that isosceles trapezoid that we're going to talk about down at the bottom. These would then have to be the same length. And again, we call the top a base, and we call the bottom a base. And we call the two sides of our trapezoids, we call these legs. So there's a leg and there's a leg over here. So one of the cool things about a trapezoid is trapezoids have what we call a mid-segment. And the mid-segment, and I'll write this out. So this, in this case, it's mid-segment B to R, is actually parallel to each base, and is actually the average of the base lengths. So let's take a look at that. Mid-segment means that this segment begins at the middle of the first leg and it ends at the middle of the second leg. So you'll notice this is equal to this, and these two pieces are equal on the right. That means this mid-segment is going to be, again, parallel with both of the bases. So we can actually treat these all like a transversal cutting through. This angle is the same as this angle is the same as this angle. These angles would be the same, so we can build off of that idea. And then its length, if I want to find the length of B to R, is actually the average between these two. So you'll notice down here it gives you a little formula. We just do 1/2 the upper base plus the lower base, or in other words, add the bases together and divide by 2. That gives us the mid-segment length, or the average. Okay, again, an isosceles trapezoid is just a little bit more specific. This is where the legs are actually congruent, and when the legs are congruent, I should have written this in as well, each pair of base angles, so the upper ones and the lower ones, like I drew in my diagram, is also congruent. Okay, and the cool thing about also isosceles trapezoids is your diagonals are congruent. Okay, so again, looking over at this diagram, that's kind of what we're talking about. Both sets of base angles, those would be congruent. These upper ones would be congruent. If I were to draw diagonals in here, they don't bisect, but they would be equivalent in length. Okay, the last one is the kite. So if we look at the kite, specifically, this one gives you that the diagonals are cutting through at a perpendicular angle. I guess I should say 90-degree angle, which is perpendicular. So the diagonals are perpendicular. Okay, and one pair of opposite angles, and I'll show you what this looks like in the diagram, are congruent. Okay, so a kite, if you look up here, is a quadrilateral where these two segments are the same length and these two segments are the same length. When that happens, again, it creates diagonals that cross at a right angle, and we will use these later when we've done some trigonometry, and we'll actually find various lengths within the trapezoid. They also have a set of opposite angles that are the same. So you'll notice this is the larger angle than this little guy over here, but these two angles are actually going to be equivalent. So when we're looking at opposite angles that are equivalent, we're talking about this one up here and this one down here. It's defined right here, angle WXY. So we're looking at WX to Y is this angle, is congruent to WZY. Okay. I'm going to stop this video right here, and then the next video I will pick up and I will do some examples that are on the back of this sheet.